Imagine trying to run a simple data processing script locally, but your VRAM instantly maxes out and crashes.
Yeah, a total nightmare.
Right. And why does it happen? Because your AI model insists on loading like 120 gigabytes of French poetry and Python coding experts into memory just to do basic math.
Exactly.
So today, we're looking at a brand new paper that actually solves this hardware bottleneck. It's called Pretraining Mixture of Experts for Emergent Modularity. It's by researchers Ryan Wang, Akshita Bhagia, and Sewon Min from UC Berkeley and AI2.
It's a huge shift.
It really is. So here is the 1-minute TLDR for you. Right now, current large language models, even mixture of expert models or MoEs, they are deployed as massive monolithic systems. To use them, you have to load the entire model into your VRAM, even if your specific task is highly narrow.
Right. And the solution these authors introduce is a model called EMO, which stands for Emergent Modularity.
Emergent Modularity, yeah.
EMO automatically organizes its internal experts by semantic domain. So it creates distinct physical pathways for health, coding, or finance using nothing but naturally occurring document boundaries during the training process.
And that's completely self-supervised.
Exactly. There's absolutely no expensive human labeling required to categorize the data.
Which is incredible. But the result that makes this paper a massive breakthrough is the deployment flexibility. When you deploy EMO, you can throw away 75% of the experts, and you only lose like 1% in absolute performance on a given domain.
It's wild.
And you can push it even further. You can throw away 87.5% of the experts, retaining only a tiny 12.5% sliver of the model. You only drop 3% in performance.
Yeah, if you attempt that kind of aggressive pruning with a standard MoE, the model's reasoning capabilities just completely break down.
These just fall apart.
Okay.
So if you are an AI researcher, an ML engineer, or a developer building the next generation of efficient models, welcome to this AI Paper podcast.
We are looking at a fundamental shift in how the industry approaches sparsity here. I mean, we're moving from models that only look sparse on a spec sheet to models that are functionally, physically modular in practice.
Okay, so we've got this incredible claim that EMO allows you to basically take a scalpel to the architecture, carve out most of the parameters, and maintain state-of-the-art performance. But theoretically, I mean, standard sparse models already only activate a small fraction of their network per token.
Right.
If a standard model has 128 experts and it only activates, say, 8 of them to process a specific word, it seems like the system should inherently be modular.
Yeah, you would think so, but that token-level sparsity creates a highly deceptive picture of the model's actual memory footprint.
How so?
Well, processing a single isolated token might only touch 8 experts, but models process sequences, sentences, paragraphs, entire code bases.
Right.
As tokens pass through a standard MoE, the routing mechanism just scatters them. By the time the network finishes processing a standard input sequence, the tokens have collectively bounced across almost all 128 experts.
Oh, wow. So you end up needing the vast majority of the network resident in memory just to handle a basic everyday prompt.
Exactly.
It's like hiring a massive kitchen staff where you assume everyone is a highly specialized independent chef.
I love this analogy, yeah.
But once this shift starts, you realize one person only chops onions, another person only handles salt, and a third guy only operates the stove dials.
Yeah.
You still need the entire 128-person staff crammed into the kitchen just to make a basic omelet.
That is exactly what is happening in the GPU.
But I struggle to understand why gradient descent distributes the parameters that way. Assuming gradient descent naturally searches for the most efficient computational pathways, why does it force the network to distribute the workload so inefficiently?
Well, the thing is, the network is optimizing for a completely different objective than modularity. Gradient descent is searching for the path of least resistance to minimize cross-entropy loss.
Right, which in a language model just means getting better at guessing the next token.
Exactly. So when you train a standard MoE with conventional load balancing across a massive, diverse internet dataset, the absolute easiest way to drive down that loss is to specialize at the syntactic level.
The syntactic level.
Yeah, the model dedicates entire experts to low-level, high-frequency linguistic mechanics. You will see an expert dedicate its entire parameter count to processing prepositions like of, in, or for.
Wait, seriously?
Yeah, and you'll see another expert that exists almost exclusively to process commas and periods.
Okay, because every sentence regardless of whether it's a research paper on quantum field theory or a recipe for chocolate chip cookies, relies on prepositions and punctuation.
Exactly. Every single input sequence is going to trigger those foundational structural experts.
So the model is functionally monolithic because the specialization is happening at the level of universal grammar, rather than the level of the specific topic.
Right. You can't just extract the quantum physics weights for a lightweight deployment because they are inextricably tangled up with universal punctuation experts that the quantum physics text happens to need.
That makes total sense. So it's a syntactic trap.
It really is. The syntactic trap prevents any meaningful extraction. If you rip out those universal grammar experts, the model loses its fundamental ability to construct a coherent sentence.
Even if all the domain knowledge is still technically present in the remaining weights.
Exactly. So to achieve true modularity, the researchers had to force the network to specialize by semantics, by the actual topic of the text.
But doing that usually requires paying human annotators millions of dollars to manually tag a trillion token dataset with category labels, right?
Usually, yes. But that brings us to EMO's core mechanism. They bypass the need for human labeling entirely by relying on a free, self-supervised signal.
Which is document boundaries.
Right, document boundaries. They operate on the assumption that tokens contained within a single file generally share a cohesive semantic domain.
Like a Wikipedia article on cellular biology is mostly going to contain biology tokens.
And a repository on GitHub is mostly going to contain Python tokens.
Okay, so how do they actually use that during training?
During the pre-training phase, EMO leverages that assumption by enforcing a strict new writing constraint.
Okay.
For any given document entering the model, the router first selects a shared pool of experts.
Meaning a highly restricted subset of the total network.
Right. So if the full model architecture contains 128 experts, EMO might restrict a specific document to a shared pool of only 32.
So every single token within that document is forced to route exclusively through that specific pool of 32 experts.
Yes.
Wow. So by walling off the rest of the network, you fundamentally break the model's ability to rely on those document-spanning universal syntactic experts.
Exactly, because it has to figure out how to process the whole document with just that pool.
But wait, let me push back on that for a second. If you restrict a document to a pool of size, sticking with the example of 32 experts out of 12018, doesn't the network just overfit to that exact capacity?
That is a very valid concern.
Because the weights would optimize themselves specifically for a 32 expert computational pathway. If an ML engineer downloads this model later and wants to deploy a heavily compressed 8-expert version for a constrained edge device, the model has never learned how to function with only 8 experts.
Right. And the authors anticipated that exact capacity bottleneck. If the hyperparameter D is fixed as a static number during training, the model severely overfits. It performs exceptionally poorly if deployed with a different expert count.
Okay, so what's the fix?
The mechanism they use to prevent this catastrophic overfitting is dynamic pool sizing.
Dynamic pool sizing.
Yeah, during pre-training, the pool size D is not a fixed integer. It is treated as a random variable sampled from a uniform distribution for every single document that passes through the training pipeline.
Oh, wow. So one document might be forced to route through a tiny pool of just 16 experts. The next document is given a massive pool of 64, and the next one gets constrained to 12.
Exactly. The minimum pool size matches the baseline number of active experts per token, which is 8, and the maximum stretches all the way to the total number of experts, 128.
So by exposing the network to this massive variance in capacity during the pre-training phase, the model learns to construct fluid representations.
Yeah, it learns how to operate effectively with subsets of wildly varying sizes. That dynamic exposure during pre-training is what provides the incredible flexibility when you finally slice the model up for deployment.
That is brilliant. Designing a dynamic routing constraint mathematically is one thing, but actually training MoEs at scale is notoriously difficult. Yep. Engineers constantly fight spiky gradients or collapsed routing where all the tokens pile into 2 favorite experts and ignore the rest of the network.
Oh, absolutely.
Injecting a strict document-level constraint seems like a recipe for training instability.
It is. The researchers ran into a severe structural conflict immediately, and the conflict stems from how massive models handle load balancing.
Okay, break that down for us.
Standard MoE implementations compute their load balancing loss locally within a microbatch. Microbatches are used because calculating loss across a small subset of data reduces cross-device communication, making distributed training across thousands of GPUs actually feasible.
Right, but a microbatch only contains a handful of documents.
Exactly. And the collision here is obvious.
Yeah, the local load balancing objective is actively pushing the network to spread the tokens uniformly across all 128 experts to ensure the hardware is fully utilized.
But EMO's new routing constraint is actively forcing all the tokens from a specific document to cluster tightly into a small shared pool of, say, 32 experts.
So you have two loss functions directly fighting each other.
Yes, it creates immense gradient spikes, turning the loss landscape into a series of sheer cliffs.
So how do you fix that?
The solution requires abandoning the local microbatch entirely. EMO utilizes global load balancing.
Global load balancing, like what they use in Qwen 3.
Exactly like Qwen 3. Instead of trying to balance the expert utilization within a tiny local context, the system aggregates the routing statistics across entire data parallel groups.
A data parallel group being the cluster of GPUs holding replicas of the model weights, processing different slices of the massive global dataset simultaneously.
Right, so by communicating the routing statistics across that cluster, the model suddenly has visibility over tens of thousands of diverse documents at once.
And looking at it globally changes the math entirely.
Exactly. One document is clustered tightly into Pool A. Another document is clustered tightly into Pool B. When you aggregate the usage across the entire data parallel group, all 128 experts are getting uniform utilization.
So the global load balancing objective is completely satisfied.
Yep. But locally, within the boundary of any single document, the tokens remain deeply clustered, satisfying EMO's modularity goals. The gradient conflict vanishes.
That is incredibly elegant. But resolving that gradient conflict stabilizes the routing squeezing distinct semantic clustering out of a standard transformer block usually requires some deep structural tuning too. Layer normalization, for instance, usually gets chaotic in sparse models at scale.
Yeah, and the team made 3 highly specific architectural adjustments to optimize the transformer blocks for this setup.
What was the first one?
The most critical is the inclusion of a shared expert. This is a dedicated expert that remains active for every single token, completely ignoring the dynamic routing constraints.
Oh, interesting. So it functions as a baseline knowledge and syntax repository.
Exactly. By offloading those universal linguistic features, the commas, the structural prepositions to the shared expert, the routed experts are freed up to specialize entirely in nuanced semantic domains.
You essentially give the model a dedicated grammar engine so it doesn't have to waste modular parameter space learning how to construct a basic sentence.
That's a great way to think about it. The second adjustment is replacing postnorm with prenorm for the layer normalization.
Because postnorm places the normalization step after the residual addition.
Right. And in an MoE, where tokens route through highly specialized, unshared weights, output magnitudes can vary wildly. Postnorm allows that variance to compound exponentially across layers, which destabilizes training.
But prenorm normalizes the inputs before they enter the attention and feed forward sublayers, keeping the gradients strictly bounded.
Exactly. It keeps things much more stable.
And the third tweak.
It involves removing a standard normalization step entirely. They completely removed QK norm, or query key normalization.
Wait, really? In standard dense models, QK norm is deployed to prevent attention scores from spiking, keeping the attention distribution smooth and high entropy. Why would removing a stabilizing mechanism actually help EMO?
Because EMO actively requires sharp, low-entropy routing.
Ah, I see.
Yeah, the experts need to confidently and aggressively claim specific semantic domains. Over-normalizing the queries and keys flattens out those distinct routing signals, making it harder for the network to sharply partition topics.
So removing QK norm allows the model to develop the aggressive contrast needed for distinct clustering.
Exactly.
Okay, so we have a model that dynamically sizes its expert tools, balances tokens globally to avoid gradient collapse, and uses an optimized architecture to encourage sharp routing. But theoretical convergence doesn't guarantee the model actually retained complex reasoning skills from its 1 trillion token pre-training diet.
Right, you still have to test it.
Yeah, this is a model with 1 billion active parameters and 14 billion total parameters. When put up against standard industry benchmarks, does EMO suffer a modularity tax?
Not at all. To establish a baseline, they evaluated EMO at full capacity, utilizing all 128 experts. It completely matches the performance of a standard, dense equivalent MoE on major evaluations like MMLU, MMLU Pro, and GSM-8K.
And those benchmarks rigorously test everything from elementary mathematics to graduate-level physics and professional law.
Yeah, EMO matches state-of-the-art performance without paying any penalty for its underlying modular structure.
Establishing that baseline is vital, but the actual promise of this architecture is what the paper calls selective expert use. The real evaluation is what happens when we start chopping the network up.
And that is where EMO radically alters the VRAM versus accuracy trade-off. When the researchers retained only 32 experts out of the original 128, EMO matched or outperformed memory-matched models that were trained entirely from scratch.
Wait, so a 32-expert slice of EMO is beating a dedicated 32-expert model that was custom-built and trained for thousands of GPU hours just to fit that exact footprint?
Yes, exactly. EMO pushes the Pareto frontier, the absolute mathematical limit of optimal efficiency. You are capturing the deep, complex knowledge compression of a 14 billion parameter pre-training run, but you're deploying it within the tiny inference footprint of a much smaller model.
And if you attempt this with a standard MoE?
If you force a standard MoE to run with only its top 32 experts, performance plummets to near random chance.
Unbelievable. For the engineers listening, though, this introduces a highly practical deployment hurdle. If I want to extract a small expert subset for a specific application, say I am building a medical QA bot for a hospital system, and I only want the medical experts, how do I map the routing to know which 32 experts to keep?
That sounds like a lot of work, right?
Yeah, gathering a massive medical validation dataset to run inference and calculate the highest probability pathways sounds like a heavy engineering lift.
Well, the sample efficiency of EMO's architecture is staggering. You do not need a massive dataset to map the routing.
Really? What do you need?
The authors demonstrated that you only need about 5 few-shot examples to accurately identify the optimal expert subset for a specific domain.
5. Just 5 simple prompt examples are enough to carve out a custom state-of-the-art sparse model from a 14 billion parameter network.
Yes. The semantic pathways are so deeply entrenched in the weights that the model's first instinct is the correct one.
That is insane.
You literally feed 5 medical QA examples into the full model, average the routing probabilities to observe which experts activate the strongest, and extract the top ones.
And that actually works.
It works flawlessly. The researchers tested multiple pruning methods. Random selection fails, but simple router-based selection, just taking that average probability, works perfectly.
Did they try anything more advanced?
Yeah, they also applied a state-of-the-art pruning algorithm called EasyEP, and EMO remained highly robust regardless of the specific selection scheme. The relevant experts practically flag themselves the moment they encounter in-domain text.
Okay, the macro-level benchmark numbers prove the selective pruning works, but the authors actually went a step further to physically map the internal representations of the network. They tracked the token routing to prove why the clustering succeeds.
They did. They conducted a comprehensive token clustering analysis. The team ran 12,000 documents through the network and extracted the routing probabilities for the tokens.
And how do you even visualize something with that many dimensions?
They used PCA, principal component analysis, to strip away the noise and squash this massive high-dimensional data into a lower dimensional space that could actually be visualized.
Got it.
And once projected, they applied spherical k-means.
Right, so spherical k-means essentially draws boundaries around data points in that dimensional space, measuring the angles between token representations to identify naturally occurring clusters. It maps exactly how the network organizes information.
Exactly.
When they applied this technique to the standard MoE baseline, the topology must have mapped perfectly to the syntactic trap we discussed earlier.
It absolutely did. The standard MoE grouped tokens into highly structural clusters, labeled things like word internal subword fragments or coordinating conjunctions and possessives and definite articles.
So it organized its parameters like a dictionary, grouping concepts purely by parts of speech.
That's exactly what it did. But when they applied that same spherical k-means analysis to EMO's routing probabilities, the topology shifted entirely.
Let me guess, EMO organizes its parameters like a library's Dewey Decimal System.
That is exactly it. The clusters were entirely semantic. They identified distinct, physically isolated regions of the network dedicated to health, medical and wellness, U.S. politics and elections, source code, and film, music, TV, and book reviews.
And just to impartially report on all the findings here, the researchers also found a distinct cluster specifically for spam, adult, and gambling content, right?
Yes, they did. The model naturally cordoned off low-quality or sensitive material into its own physical region of the network, based purely on the statistical distribution of the training data.
That is fascinating.
And they rigorously verified the integrity of these clusters using Web Organizer, which is a data set containing 24 human-labeled domains.
What did that show?
Running a cosine similarity analysis revealed that EMO creates massive separation between unrelated domains. A medical document and a Python script have almost zero overlap in the routed experts they trigger.
Wow.
And interestingly, this semantic separation becomes significantly sharper in the deeper layers of the transformer architecture.
Oh, because the early layers handle basic structural processing, while the deeper layers aggressively partition the tokens by topic.
Exactly.
The immediate implication for the developers and engineers listening right now revolves around deployment scaling. As the industry pushes foundational models toward trillions of parameters, serving them becomes a severe VRAM bottleneck.
It is the biggest bottleneck right now.
But EMO provides an entirely orthogonal path to efficiency. Instead of aggressively quantizing a monolithic model and degrading its reasoning capabilities, you can selectively deploy the 10% of the network that actually pertains to the user's specific workflow.
Yeah, it introduces an unprecedented level of structural control over the network. Because EMO physically maps experts to semantic concepts, you can literally disable specific model behaviors at the architecture level.
Right, returning to that spam and adult content cluster.
Right.
If you were developing a child-safe educational application, you no longer have to rely on brittle system prompts or expensive reinforcement, learning from human feedback pipelines to guardrail the model.
No, you don't. You can physically delete the experts containing the sensitive content before deployment.
It shifts the entire paradigm from behavioral safety to structural safety.
It really does. It turns an opaque, monolithic black box into a composable toolkit.
It really does. But here's a final provocative thought to leave you with. We started by looking at the frustration of a sprawling 128-person kitchen staff where no one can cook an entire meal. EMO reorganized that kitchen into highly capable, specialized teams.
Beautifully put.
But it achieved all of this relying on a single, completely free, naturally occurring signal: document boundaries.
Yeah.
Knowing where a text file starts and ends was enough to force self-supervised modularity.
Right.
So what other hidden metadata could we use as structural constraints during training? What happens if we force routing based on the timestamp of an article? Could we build a model where we physically sever its outdated knowledge by simply dropping the 2021 experts from the architecture?
Oh, that would be incredible.
Or what if we route based on the ID of the author? Could we force entirely new, controllable architectures in the future just by listening to the structural whispers already hiding in our datasets? It is a fascinating frontier.
The monolithic wall is finally starting to crack.
It really is. Thank you for joining us for this AI Paper podcast. Keep building, and we'll see you next time.